So this is technically lecture 11, which is the worksheet. Oops, what happened? I just lost my my iPad. I have to get it back. So let me pause the recording. Okay. So for those of you who are joining us not live, I forgot to start the recording, but what you see, the first slide is the first problem. Okay, so now we move on to the second problem, which is, let me clear my drawing, which is the problem of integrating cosine, e to the 3x times sine of 5x dx. Now, when setting this up, this is going to pretty much be clear to you. It should be an integration by parts problem, right? So the question is, what is u and what is dv? Whatever you choose for u, the rest of the integrand has to be dv. So now there are basically two choices. We can let u be e to the 3x, or we can let u equals sine 5x, right? Uh, I don't think really for this kind of problem, there's an advantage of doing either or. So I'll just go with the second one. So I'm going to go with sine 5x. It's not any easier to do it either way. I'm just partial to that. So u is sine 5x. Okay, so that means dv is everything else, which is e to the 3x dx. Okay, so now we have to take du, which is the derivative times dx, which is 5 cosine 5x times dx. And that dx must be there because it's usually you would write this in as a derivative as du over dx equals 5 cosine 5x. What I've done is I brought the dx over to the right-hand side. I've made the equation look like that. And this is called, as I said in my lectures, differential form. This is called a differential. Okay, now dv is e to the 3x. That means v is the antiderivative of e to the 3x. So you guess that it should have something again to do with e to the 3x. But you want to put a factor there to make sure you get the right derivative. See, the derivative of e to the 3x is 3 times e to the 3x. And we don't want to get a 3 times e to the 3x. We want to get just an e to the 3x. So if we rescale our guess for v by a third, then the derivative of what we get, 1/3 e to the 3x will be e to the 3x. So that's why the 1/3 is there. It's called a fudge factor, or just a fudge constant, if you like. Okay, so that's the setup. And now, if we want to actually write down the integration by parts formula, we have to take u times v, which is 1/3 e to the 3x times sine 5x. I wrote v times u, but that's the same, minus the integral of, well, I'm going to bring the constants out. We have a 5, and we have a 1/3. That builds a 5/3 on the outside of the integral sign. And then what's left over, excuse me, is e to the 3x times cosine of 5x dx. Okay? All right. So excuse me, I'm going to get a tissue. Okay, that's better. So now it doesn't look like we've gotten any mileage out of this because now we have this integral here to deal with, and it doesn't look any better. But in fact, we can do the same thing again. So what I'm going to do is repeat what I did with the previous integral, and you'll see that magic occurs. So so if this was this is step 1. Step 2 would be let u equal cosine of 5x. I'm doing pretty much exactly the same thing. then du is minus 5 sine 5x dx. And then dv is e to the 3x dx. So v is 1/9 e to the 3x. And so we're able to then write the integral of e to the 3x times cosine of 5x as u times v, which is 1/9 e to the 3x times cosine of 5x, minus the integral of, okay, so the constant is negative 5/9, so that's going to turn the minus sign into a plus sign. So, and it's going to be a 5/9. And then there's going to be e to the 3x times sine of 5x dx appearing. Okay, any questions so far? Okay, you could also ask me a question in the chat if you're nervous about talking on here. Okay, that's fine also.
I have a
All right,
question.
yes, go ahead.
I understood how you got the 1/3 in front of the e, but in front of the e to the 3x, but I'm a little confused on how you got the 1/9. Could you explain
Oh,
that?
okay, well, it's the same thing. There was a 1/3, oops, I messed up. That is, you know, I made a mistake, and thank you for pointing that out. So it is, I should not be a 1/9, it should be a 1/3. So I'm going to erase the 1/9, put a 1/3 there, and that comes at the expense also of changing the constant here. It's going to be 5/3. Better?
Yeah, thanks.
Okay, thank you for catching that. I make mistakes, especially with, I have like at least 4 pieces of technology I'm using in front of me right now. I got my desktop, I got my iPad, I got my keyboard, I have my mouse, and I have my pen, right? My Apple pen. So
That's all good.
so it's like, and they have to all be sort of coordinated properly. And it's just very, if you have, if you're not good at multitasking, it's kind of a disaster, right?
And so
Okay,
would that first 1/9 to the e to the 3x also change?
that should be a 1/3.
Okay.
Okay, we're better now, I think. Okay, so now the plan is to just substitute this expression into here. So I'm going to do that now. So we're going to get the integral, the left side of the equation, the top line is the integral of e to the 3x dx, sine 5x dx, is equal to 1/3 e to the 3x times sine 5x, okay, minus 5/3. And then we have to substitute in the value of the integral that we got. So that would be 1/3 e to the 3x times cosine of 5x. Okay, and then we have plus 5/3. And then the integral of e to the 3x times sine of 5x times dx, close parentheses. Okay, so that's all very well and good and so far, but now I want to bring this term that appears on this side, this one here, over to the left side because it's a like term. So in order for me to do that, I'm going to have to erase a portion of the screen to make more room. So what I'm going to do is I'm going to save this slide first. And if I can find my options here. Oh, here we go. Okay, and I'm going to erase a portion of the screen. Okay, so I'm going to write the answer then in the erased portion. So the answer, well, first of all, what is the constant on the right in front of the integral that appears? Well, there's a 5/3 that appears, this 5/3 over here, but there's also a minus 5/3 that appears from here. So that if you multiply those together, what do you get? you're going to get negative 5/9. So in other words, the integral of e to the 3x sine 5x dx is equal to, okay, so let me combine the first two terms, this one and this one with the constant in front of it, together. So that will be 1/3 e to the 3x sine 5x minus 5/9 e to the 3x cosine of 5x. And then I think I'm going to need to get rid of this arrow here. Okay, so that takes care of this term and this term. And what's left over is the integral, which has a minus 5/9, the integral of e to the 3x times sine 5x dx. Okay, so that's what you have, but you're not done. I wanted to
Excuse me,
get this.
Professor.
Yes.
Should it be a negative 25/9 if you're doing
Oops,
like
25/9. Yes, 25/9. And is that the only place? Yeah, that's the only place. Okay. So now I want to bring that negative 25/9 over times the integral over to the left side. So you're going to get 1 plus 25/9 times the integral of e to the 3x sine of 5x dx equals 1/3 e to the 3x times sine of 5x minus 5/9 e to the 3x cosine of 5x. Am I good still? Is it correct from your end? Okay, I don't think I made another mistake. Okay, so now I want to solve the problem. So first of all, what is 1 plus 25/9? Well, that's 25. That's 9/9 plus 25/9, which is 34/9. So 1 plus 25/9, I'll write that here, is 34/9. In order to divide by that, I have to divide both sides by 34/9, which is the same thing as multiplying by 9 over 34. So the final answer is the integral of e to the 3x times sine of 5x dx equals 34/9, 9/34, sorry, times 1/3 e to the 3x. And there should be a plus c somewhere. We're going to do that at the end, though. Plus c. Okay, so now there's some simplification, which one really ought to do here, because the 1/3 and the 9/34 builds for you a cancels to be 3/34 times e to the 3x sine 5x minus, it looks like 5/34 e to the 3x cosine of 5x. Okay, and then there's a plus c to deal with. Okay, so this is the final answer to the problem. Okay, so that was a bit longish, this problem, I admit. So let me save the screen. Okay, so shall we move on to problem 3? We good? Okay, so problem 3. Okay, so problem 3, we actually kind of had a version of that in class, but there are two ways to do this problem now. So method 1, we can use integration by parts. That's what the hint is basically given to you as. We can let u be, let's see, I said let u be cosine. Well, I'm going to think of this as cosine of x times cosine of x dx. So we can let u be cosine of x. Oops. Is that going to work? Let's see. So, wow, this is not going to work. I don't think this is going to work. because if you let u be cosine x, then du is sine x. That's not going to work. So this is the hint is bad. Don't use the hint. Don't use the hint, or at least I don't remember why the hint was put there. I wrote this worksheet about 5 years ago, by the way, and I just like recycled it. Okay, so what you should be using is the trig identity, cosine squared of x. Yeah, so there's this double angle formula. It's 1 plus cosine of 2x all divided by 2. So that's what you should be using to do this. And so I will not write it the way it was written. So now this becomes the integral of 1/2. I'll bring the 1/2 out of 1 plus cosine of 2x dx. Okay, and this breaks up into two separate integral. One of them, which is 1 times dx, whose antiderivative is x. I'll just do this integration all at once. Okay, so it's 1/2. The antiderivative of 1 is x. And then the antiderivative of cosine of 2x, what could that be? Well, your initial guess might be sine of 2x. But that would not be quite correct because the derivative of sine of 2x is twice cosine 2x. So we have to put in a fudge factor, and the correct fudge factor to put in is 1/2. If you take the derivative of 1/2 sine 2x, you'll get cosine of 2x. And then I guess I don't need this parentheses anymore. And so, and then we have to add a c. So that's the solution to that problem. Any questions? So if not, let's move on. Okay.
What's that formula called? The cosine squared x?
This thing is called it's one of the double angle formulas.
Okay.
There are basically 3 or 4 of them. Okay. So there's one for sine squared x, which is 1 minus cosine of 2x over 2. And then there's actually one for secant and tangent also, but I'm not going to write that down here. But these are the two which come up the most often. There's also one you probably have seen it. Sine of 2x is 2 sine x cosine of x, right? So if we divide both, so you can express, in other words, sine x cosine of x as 1/2 sine x cosine of x. I'm sorry, I didn't write that correctly. Blah. Sine of x times cosine of x is 1/2 sine of 2x. So these are the 3 double angle formulas that are actually, the book lists them also if you look in the book in that section. Okay, so that is, we don't need this number 1 either. So I'm going to save the screen.
I have a quick question.
Sure.
At the end, after you use the double angle formula, I don't understand how you did like the integral. I don't know. Maybe I just
okay.
can't read it.
So I went too quickly then, maybe. So I broke up the integral as, see, there's a 1 and then there's a cosine of 2x that appears, right? So
Yeah.
So let me put it over here. So that's 1/2 the integral of 1 dx plus 1/2 the integral of cosine of 2x dx, correct?
Yeah. And then it ends up becoming like x. After you
So,
integrate it, the 1 becomes an x.
so it's x over 2, right?
Yeah.
And the other is the integral of 1/2. Oops, there's another typo, or actually it's a mistake. The derivative, I actually just computed the antiderivative of cosine of 2x, but there's a half in front of this. See the 1/2?
Yeah.
So
That's
we
why I
have
was
to
like wondering.
so we have to put a quarter here, actually, I believe, to make this work out, right? So it's a quarter sine 2x plus c. Okay, so that's, thank you for pointing that out because there was a typo. Okay?
Yeah. Thank you.
Okay, good. All right, so I'm going to move on to the next problem, which is number 4. And let me clear the screen to do that. Okay, so number 4, it's the integral of secant fourth x dx. Okay, so the suggestion, if you go back to the hint in the text that it gives you to deal with an integral like this, it suggests taking secants to the fourth and breaking off a secant squared and combining that with the dx. And now we convert the other secant squared, the one that's remaining, everything else that's remaining, into a tangent. So what does that mean? That means, remember that secant squared minus tangent squared, secant squared x minus tangent squared x is equal to 1. So therefore, secant squared x is equal to 1 plus tangent squared of x. So I'm going to get a 1 plus tangent squared x here. And then there's a secant squared x dx. And the advantage of that is now we can let u be tangent of x. And then we're just going to do this trig substitution. And then du is secant squared of x dx. And then it's the integral of 1 plus u squared du. This is the du portion. This is 1 plus u squared that appears. So then the integral becomes u plus u cubed over 3 plus c. And we go back and we substitute the original value of u, which is tan x plus tangent cubed of x over 3 plus c. This one wasn't bad at all, right? Okay, so let me save the screen and move on to the next problem, unless we have a question. No questions? Okay, so let me get rid of it. Okay, and we're at problem 5 now. So problem 5 is to integrate the integral of 1 over x times the square root of 4 minus x squared dx. Okay, so if you go to the section of the book, this is the section which it gives you a suitable trigonometric substitution. If you follow the recipe there, the right thing to do is to let x equal 2 tangent theta. You look at the square root, and that is not correct. It's 2 sine theta. So if you have the square root of a squared minus x squared, that would be x equals a sine theta. That was the first one. And then if you have a squared plus x squared, x was a tangent theta. And if you had the square root of x squared minus a squared, you got x equals a secant of theta. These are the 3 substitutions in that section. Okay, so we're going to let x equal 2 sine of theta. Then dx is equal to 2 cosine of theta d theta. And we have to rewrite the integral in terms of theta now. And how are we going to do that? Well, we have dx over here. We have to put that in. So dx is 2 cosine of theta d theta. That takes care of the dx appearing in the integrand above. Now we have to take care of the x. What's x? It's 2 sine of theta. And then we have this square root to deal with. And the point is that when you plug 2 sine theta in for x, you get 4 minus 4 sine squared theta for 4 minus x squared. And that's the same as 4 times 1 minus sine squared of theta, which is 4 times cosine squared of theta. And we're going to take the square root of that. And when we take the square root of that, we get 2 cosine of theta appearing. Everybody follow me so far? If you don't want to talk, you could always use your, there's usually on most people's Zoom screen a reaction button, and you can do this. Okay?
I'm sorry, I can't read where you have the 3 equal signs on top of each other, what that last one says there.
Oh, that's 4 cosine squared of theta. I'll rewrite it. This one here?
Yes.
Okay.
Thank you.
Okay, so I took the square root of that because we have a square root to get 2 cosine of theta appearing, right?
Right.
Okay, so now there's cancellation. And we get what's left over. I'm going to bring the half, the factor of 1/2 out. And it's d theta over sine theta that appears, which is the same as 1/2 the integral of cosecant theta d theta. That's the definition of cosecant, is 1 over sine. Okay, so now we have to remember what the antiderivative of cosecant is, right? And actually we haven't done that, unfortunately, but I can tell you what the answer is, or we can do it later. So what I'm going to do is I'm going to defer the answer here. This answer is deferred. It's closely related to something we did do already. I'm not going to do it now. So it's related to the integral for secant theta, d theta, which is the same thing as ln of secant theta plus tangent theta plus c. So I'll tell you the answer. There's going to be a minus sign in front of the ln for the cosecant case, and instead of secant, you're going to have a cosecant, and instead of a tangent, you're going to have a cotangent. So what I'll do is I'll write the answer to the integral of cosecant theta on the top of the screen, and then we'll see why that's true later. It's unfortunate that I gave something that we didn't do yet. So it's minus ln, unless I am remembering wrong, cosecant theta plus cotangent theta plus c. So you're going to have to multiply that by 1/2, and that will be your answer. So let me save the screen because there's no more. Well, I'm going to save the screen. And then what I'm going to do is I'm going to erase this, and I'll write the answer, but it'll be based on something we haven't done yet. So I'm going to bring this down here, and I'll get 1 minus 1/2 cosecant of theta plus cotangent of theta plus c. Okay, so let's leave it at that, and I'll tell you how to do the integral of cosecant theta at the end if there's time. Okay. All right. If I don't get it at the end today, I'll do it in my my next lecture. I promise you. Okay. Okay. So let's move on then. Okay. So let's go to problem number 6.
Professor,
Yes.
for number 5, isn't it because it's a trigonometric substitution? Would you have to substitute the x back into the, like, replacing the cosecant
Oops.
and the
Yeah.
cotangent?
I'm getting like sidetracked. Okay. So let's go and do that. Okay. Very good. Excellent. Okay. So let me erase and get more. We have to figure this out, obviously, right? Okay. So our substitution was, recall, x equals 2 sine of theta. That's the key thing here, right? We have to figure out what cosecant theta is, and we have to figure out what cotangent of theta is. So it's better in order to do that, it's better to write sine theta as x over 2. And to think of x as, you have a right triangle where theta appears as the angle. And if sine of theta is x over 2, then if we let x be the opposite side, then the hypotenuse must be 2, correct? So therefore, the adjacent side is the square root of 4 minus x squared. And from that, we can actually figure out what cosecant theta is and cotangent theta is. Cosecant theta is 1 over sine. So therefore, it's hypotenuse over adjacent. So cosecant of theta is 2 over x. And cotangent of theta is, since tangent theta is opposite over adjacent, cotangent is adjacent over opposite. So it's the square root of 4 minus x squared over x. So, so we're now in a position to write the final answer, and thank you for pointing that out. It looks like it's 2 minus a half ln 2 over x plus the square root of 4 minus x squared over x, absolute value plus c. So that's good. Okay. Other questions before we move on? Okay. So I'll move on. Okay, so let me clear the screen. And now we get to problem number 6, which is to integrate dx over the square root of 2 plus 3x squared. Now the trick with this is to think of 2 plus 3x squared in the following way. I want to write this as a squared plus x squared, sort of, right? So what do I mean by that? I'm going to think of this as the square root of 2 quantities squared plus the square root of 3x quantities squared. So the a would be the square root of 2, and the other term would be not x, but the square root of 3x. So what that tells me is that the substitution is to let the square root of 3x equal, well, this would be the tangent substitution. So it would be a tangent theta, so the square root of 3 times the tangent of theta. Does everybody see what I did?
What's under the square root and over the equal sign? Is that 3? 1/3.
No, I wrote the square root of 3 times x should be, it's actually the square root of 2. Sorry.
Okay, that's okay.
Right, a is the square root of 2. Remember, it's like the variable is equal to a tangent theta, right? The variable is usually x, but now the variable is really the square root of 3 times x. Now, it is convenient for now to solve for x. If you divide both sides by the square root of 3, you'll see the square root of 2/3 tangent theta is actually x. Okay, so now I'm ready to do my substitution, and this is the integral. Okay, so I have to take dx, which is the square root of 2/3 secant squared theta d theta. And so we're going to get the square root of 2/3 in the numerator, secant squared theta d theta. And what's the bottom? Well, the bottom, if you work it out, 2 plus 3x squared, if you work it out, it's going to exchange this tangent, this tangent with its constant for the corresponding secant with the same constant. So it would be the square root of 2/3 secant theta. If you want me to work it out, I'll work it out, because I think, you have to convince yourself that what I did is correct. So I'm going to say take 2 plus 3x squared. So what is 2 plus 3x squared? Well, it's 2 plus 3 times the square of 2/3 tangent theta, square root of 2/3 tangent theta. And if you work out what you get, you're going to get 2. The square. So when you square everything inside, you're going to get 3 times 2/3 times tangent squared theta appearing, and the 3's cancel, and you're going to get the square root of 1 times 1 plus tangent squared theta. And I think I messed this up, what I claimed. So this would be secant. It'll be secant theta. So there's no constant here. That was too fast. Okay. All right. So so that's what you get when you do the substitution. So it pays not to skip steps. Every time I've skipped a step today, I messed up my arithmetic, right? So it's good not to skip steps. Okay. Did I get this right? Can anybody verify for me that this looks correct so far?
What happened to the twos that were underneath the square root?
The twos that were underneath the square root.
Like the 2 plus, and then you canceled out the 3s.
Okay,
out
so
of
when
the
you
2
square the square root of 2/3, you get 2/3, right?
Right.
So it's 3 times 2/3, which gives you a 2, right? And this is a 2 here, I'm sorry. That's right, okay. I'm making lots of mistakes. Okay, so this should be the square root of 2 here.
Okay, thank you.
Okay, good, you caught me. All right, so excellent. Okay, so now the square root of 2/3 divided by the square root of 2 should be the square root of 1/3, I guess, correct? And so I'm combining the constants, simplifying, and then you're left with the integral of secant theta d theta. And I can bring the square root of 1/3 out, which I will. And then the integral of secant theta appears, which we've done in class several times, as ln of secant theta plus tangent theta plus c. Okay, so I'm going to save the screen and then clear some of the screen off so I can finish the problem, okay? We just have to remember what x was, which I should not have erased. X is the square root of 2/3 tangent theta, I believe, right? Okay, so in all these problems, you're going to end up having to draw a right triangle. So theta is here. X is, so what is tangent theta? Well, I have to solve for tangent theta to do this. So it looks like it's the square root of 3/2. I multiply both sides by the reciprocal of the square root of 2/3 to get to solve for tangent theta. And so I can put the square root of 3/2 x here. So we opposite over adjacent. You could put a 1 here. And then what is the hypotenuse? That's the by the Pythagorean theorem, this 1 squared plus 9 3/2 x squared. So let me simplify that. It's the square root of 1 plus 3/2 x squared. It looks right to me. Okay, so then we need to write down what this is in terms of x. So we have the square root of 1/3. What is secant theta? It is hypotenuse over adjacent, so that's the square root of 1 plus 3/2 x squared, plus the tangent of theta, which is opposite over adjacent, so that's the square root of 3/2 x, absolute value plus c. So I believe that this is correct, unless I made another stupid mistake. Are we good? Questions? If we're good, I'm going to move on, okay? Okay, thank you. All right, so let's move on to the last question, which is the integral of dx over x squared minus 5x. Okay, I hope we can do this problem. I don't know. You know, I took this from an old worksheet, and I'm not sure we'll see if the technique that I'm going to apply to this actually works. It may or may not apply, okay? All right, so I want to take, there's no square root here. That's the problem. So, but I'm going to still do what I did if there were a square root. I'm going to actually complete the square. So what happens when we complete the square? So we take the middle term, 5, divide it by 2, and square it. So that's negative 5 halves squared, which is 25 quarters. So now I've added 25 quarters to x squared minus 5x. I better subtract it off again. And this becomes x minus 5 halves quantities squared plus minus 25 quarters. Okay, so what would the advantage of that be? I'm not sure this is going to work out. So this might be from the next section of the text we're covering, in fact. But let's see. So what are we going to do? We're going to let, this is like one of those problems with x squared minus a squared, where a is given by 5 halves. Okay, so I'm going to let x minus 5 halves, that's the stuff inside the square of the variable, I'm going to let that be equal to 5 halves. And this is a secant substitution according to what I wrote at the beginning of today. I'm not sure this is going to work out, but I want to try it anyway. Okay, so then what is dx? So I'm going to take the derivative of both sides with respect to x. The constant disappears, so dx is 5 halves secant theta tangent theta d theta. Okay, and then what is x squared minus 5x going to be? Well, let's see what it is. Okay, so yeah, so what is it? It's going to be, well, let me first substitute the numerator in. So it's 5 halves secant theta tangent theta d theta. Now x minus 5 halves is 5 halves secant theta. So if I take x minus 5 halves squared and subtract off 25 quarters, which is what I have over here, which is supposed to be the same as x squared minus 5x, I'm going to get the square of 5 halves secant theta, which is 25 quarters secant squared theta. And then we have to subtract off the 25 quarters, and this becomes 25 quarters times tangent squared theta by the trig identity. Okay, I don't think this is the best way to do this, but I'm going to still see if we can get anywhere with it. So we have 25 quarters tangent squared theta appearing here. And I do not recommend, once we do the next lecture, lecture 11, solving the problem this way. I'm just seeing if I can get anywhere with this. Okay, so this is a hard problem. It's like overly difficult, but I'm going to do it because I'm very stubborn. I like to bang my head against the wall. Okay. Okay, so let's see. Let's do the simplify. Let's simplify. So if we simplify, we get 5 halves over 25 quarters, which I believe is 5 halves. Okay, and then the secant theta tangent theta over tangent squared theta looks like the integral of secant theta over tangent theta d theta. And where are we going with this? Well, I could bring the 5 halves out. And the only thing I know how to do at this point is to just turn it into sines and cosines. So secant theta is 1 over cosine theta. And tangent theta is sine theta over cosine of theta. And then there's a d theta. And what do we get? We get 5 halves the integral. Okay, so the cosines cancel. And we get 1 over sine theta, which is cosecant theta d theta. oh, we have the same integral we had before, which I said I would have to do later, right? So I think I owe you the calculation of this integral, which I said was minus ln of cosecant theta plus cotangent theta plus c. So, and we could add the c on the outside because it's just a constant. So let me rewrite it like this, minus 5/2 plus c. Okay, we have to also convert everything back to theta, back to x, right? So remember that we let x minus 5/2 equal, what was it? What did I write? What was the original substitution? It's not in front of me anymore. Maybe it was, I don't remember. Secant theta? Was that what it was? Or is it x plus 5/2? I think it was this. Maybe, I don't remember. Okay, so here's what I'm going to do. I'm not going to do this part of the problem. This is not the way to do the problem. Even though we can solve the problem this way, because I'm going to show you how you can, it's just overly complicated. We're going to see next time there's a much easier way to do this. And that's in the next section. However, I'm going to at least show you why the integral of cosecant theta is what I claimed it is. So let me clear the screen.
Wouldn't
Yes?
the you erased it, but like wouldn't the constant be 2/5 instead of 5/2?
The constant I have over here, 5/2, it's 5/2 over 25 quarters. Yes, it should be 1/5/2. So it should be 2/5, right?
Yeah.
2/5, 2/5.
It's a small thing. It happens to me too when I'm like doing
Yeah,
the work.
it's sort of like much more difficult to do this on a on electronically than it is in front of a blackboard. You'll see.
Fair.
So you
I
gotta.
still don't get how you got the 25 quarters though.
That's the square of. Oh, okay. So let me explain that. So this was. I computed x squared minus 5x. We had a substitution. And I don't remember what it is because it's on some previous slide. Maybe I can find the previous slide. No, I can't find the previous slide. So I'd have to look on the previous slide. What our original substitute was? It x plus 5/2 equals what? What was our original substitution in this problem? I'll try to pull it up. I got to go to my folder though, where the Zoom stuff is, because it just saves it for me. No, that's no good. 1 second. Okay, so it's probably, oops. Okay, so it's probably somewhere here. Let's see, number 25. It was, nope, not that one. Nope, 55. Nope, 56. It saves, when I saved the screen, it saved as a ping file. Okay, so I think, okay, here we go. It's x equals the square root of 2/3 tangent theta. Was that it? No, that wasn't it. That wasn't right. Did I save it? I hope I saved it. It was, I didn't save the substitution, unfortunately, so I don't remember what it was. I'd have to figure it out again. Okay, so let me figure out what the substitution is again to explain why we got the 25 quarters tangent squared theta over here. Okay, so let me do that. Okay, so how do we, where is that coming from? Well, Huh. Okay, so let me, if you'll be patient with me, I'm going to erase some of this screen here. And let's recall, so what I did. So I completed the square. I wrote x squared minus 5x is equal to x minus 5 halves squared plus 25 quarters. And then I use the, this is like an a squared plus x squared type substitution. So it would be, if you think of this as a different x minus 5 halves as playing the role of x, then it would be x minus 5 halves equals a is the square of 5 halves, tangent theta. That was the original substitution I should have made, right? That's the substitution. Now, when I do that and I compute x squared minus 5x in terms of theta, that means I have to stick in, that's the same thing as x minus 5 halves, quantity squared plus 25 quarters. So what I'm going to do is I'm going to stick in 5 halves tangent theta in place of x minus 5 halves. So what do you get? You get 5 halves tangent theta, quantity squared, plus 25 quarters appearing, and that's 25 quarters tangent squared theta. Let me factor out the 25 quarters plus 1, and that's 25 quarters secant squared theta. So that's where it came from when I substituted. Did I write that? Maybe I messed that up. Maybe that's messed up. Let's see. So it looks like that is messed up. Okay, so let's see. So dx. So yeah. So this would be secant squared theta. Okay. So let's see if what this simplifies to. It probably doesn't work again, but let's see what we get. It's the integral. Okay, so it's 1 over 5 halves, which is 2/5, as was pointed out. The secant in the numerator cancels with the power of secant in the denominator to leave tangent theta over secant theta, d theta. I think that's what I had before, in fact, right? Maybe not. So this is then 2/5 sine theta over cosine of theta divided by secant theta, which is, dividing by secant theta is like multiplying by 1 over cosine of theta. Ah, okay. D theta. And this becomes 2/5 the integral of sine theta, sine of theta, sorry, not sine squared of theta, over cosine squared theta d theta. And I'll be honest with you, this integral cannot, you can try what you want with this integral and you're not going to get anywhere with it until we do the next section. We're stuck. We're just stuck with this, okay? You had a question?
No, I was just saying, like, yeah, I like somewhat understand it now.
You somewhat understanding now? I didn't catch that, sorry. What did you say?
Sorry, my microphone died.
Okay, so what did you say?
I was just saying that, like, how, like, yeah, I understand, like, why, like, there isn't, like, why that's the furthest you could go.
Right. So what this wasn't a complete waste of time, even though we didn't get anywhere with it. It just goes to show you that you have a bunch of tools that we develop one step at a time for doing different kinds of integrals. And those tools have limitations. And eventually, with the existing set of tools, you're going to get stuck. Every time you introduce a new tool, you can actually go a little bit further. And now here's the big secret, the dirty lie they don't tell you in calculus, usually. I'm going to teach you all the tools that basically I know, and the vast majority of integrals that arise in physics, for example, and engineering, you're not going to be able to solve, even with all of these tools. It's just a certain, you need to know these tools to do certain integrals, but you're going to, but in the real world, the integrals that actually arise cannot be solved this way, right? That's the that's just a dirty fact of life. Anyway, we will be able to solve this problem next time in the next lecture. This is called integration. It'll be called integration of rational functions. That's the technique that will be taught next. And you'll see that this is a relatively easy integral to do that way, but you can't do it. It's not possible to do it any other way. Okay, so the hour is up, and I just want to, so I'm not going to do the cosecant integral. I'm going to do it in class next time. So I think I'm going to stop here unless there are any other questions. Any other questions?
I wanted to ask, so besides like this office hour or like the ones that you like announce that you want to do office hours, you also do like the one-on-one appointments too?
Yeah, that's going to be harder to do. I mean, like, I don't want to do that too often because as it is, I can do that once in a while, but I feel like it's, I'll try to, let me explain something that I have actually told at least one student. It turns out, even though I'm not commuting downtown to go to work 4 days a week, just doing this in this particular format, like just uploading videos, processing videos, is actually taking like double the amount of time it usually takes me to teach this course. And I'm very, very time constrained because of that, right? So I would prefer it that if you have like a question involving a problem, that you go to the Math Resource Center. If you have a specific sort of set of, if you're having issues with whatever issues you may be having that are content related, because they're really there for you. And I don't know if you've ever used them before, but they're pretty well trained, those people. I'm willing. I don't mind doing this group office hour. I think it's a good idea because I get feedback from you guys, and I sort of try to figure out what's going on with the course this way. But if I were to sort of do an office hour with every student that asks me, that is going to be just impossible because an office hour, I mean, even during a regular term, when you don't have a pandemic, you just sit in your office hour 1 hour a week, and you don't usually have any other office hours. That's a pretty standard thing for professors. So I would prefer not to have a private office hour unless it's sort of an emergency. Okay?
Okay.
All right. I'm willing to do it if it's an emergency, but I would prefer not to. Any other questions?
I had a question.
Yes.
So is this gonna be like a recurring thing that you do, this like group office hour?
Yeah, but I'm not going to necessarily do worksheets. The next office hour I'm planning to do, this was like a pilot run. The next worksheet I'm planning to do, I'm planning to just record the answers. The next office hour, I'm just going to ask you to ask me questions, and then I'll try to solve your questions. So in order for you to prepare yourself at the next office hour, I suggest you come to me with questions. Either from the text, or we can do it in such a way that you could, if you have a whiteboard screen on your version of Zoom, most people do, you could actually write the question down for me and I can try to solve it. We can collaborate, sort of. Okay?
Okay, and then are these office hours gonna be the same time every time, or are you gonna like change it around? Because some students I know, like they can't make it because of other classes.
I know. I'm willing to change it around, like maybe every other week we can do it at a different time, somehow on Thursday. Maybe that would be the best thing. We can try to, but I guarantee even if I change it, there'll be plenty of students who can't make it also. You know what I mean? Like I looked at what people put in in the survey, and it's just all over the place.
Okay.
Okay, but I can vary the times. That's not a problem. But I don't want to vary too many times. It just gets too confusing. Okay?
Okay. Yeah.
What
Thank
would
you.
be a good time for you?
Mine, I think anytime Thursday, I'm free. I don't
Okay,
have any
so
classes on Thursday.
I mean, I guess we could do it on at an evening time. That's another possibility. Because most people are free on in the evening. But I didn't even get like many responses for the evening either, right? So if I did it at like 8 o'clock at night, I could do it. It's not impossible to do. How many people that are here now, by a show of hands, using the reaction button, using your finger upward, put your finger up if you can make an 8 o'clock in the evening time for an office hour on Thursdays? 2 of you? How many? Let's see. 3 of you. Okay, so some of you can, not all of you. So, and hopefully when I feel more confident with, the technology, I'll be making fewer whiteboard mistakes also. So it's just a learning curve that's involved with this. Anyway,
Just a comment. I also think it doesn't matter too much if people can attend the live sessions because they are recorded.
right. Well, if they want to ask a specific question, though, it won't get asked, probably. What they could do is if they know somebody else who's going to be at the session, they could ask that person the question and I can go over it. That's another way to do it.
Yeah.
So maybe that's the way we should run that. That's a possibility. Okay? All right. I think we should end here then because it's 7 minutes over. And
Thank
I want,
you.
yeah, have a good one. I'm not putting up any other lectures except this recording this week. We're done for the week, okay?
Okay.
Okay, great. Take care. Have a good weekend.
You
Bye-bye.
You
too.
too. Bye.
You too. Bye-bye. Thank you.
Thank you.